in the simulation, we have to solve this big matrix equation for all the unknown dipoles. And it's going to be really computationally expensive, which is why these sort of higher fidelity models aren't used often. So we put a lot of work into developing a really efficient numerical method and then putting that method in a parallel form on the GPUs. And so we're able to actually do these calculations in essentially linear time, which gives us a way to use a higher fidelity model, but basically no extra computational costs. So with an undergraduate student researcher, Deep, he used this model to run lots of simulations. We answered the same question as before. What critical field strength do we need to induce crystallization, now with a more accurate model? And we can see that these predictions, these mutual dipole predictions, agree really, really well with the experiments, essentially perfect agreements. This indicates that this is the sort of level of physics that are involved in modeling field-directed self-assembly. Okay. So to accompany these simulation results, we also developed a thermodynamic theory that constructs an expression for the free energy of the dispersion at constant temperature and field, which is the actual experimental boundary conditions. This free energy has a contribution, an entropic contribution from a hard sphere reference state, and an energetic contribution from the dipoles. And so where this is minimizing this energy basically predicts the outcome of the simulations. This is really good at modeling phase separation, like what's observed here from a simulation, and also here's an experimental snapshot. By the way, I should mention that in all these images, these are all three-dimensional simulations like this, but we're always looking down the field axis, so you only see a two-dimensional projection. It's a little bit easier to tell what's going on in this view. Anyway, okay, so this sort of theory is good at modeling phase separation. In particular, minimizing the free energy in the dispersion can tell you whether or not phase separation occurs. And if it does, what the nature of these two self-assembled phases are. This can be summarized in this phase diagram here, which shows different coexisting volume fractions for any given field strength. So I first want to point out that the theory, which is in the solid line, agrees very, very well with the phase separation we observed in our simulation. So I think we're pretty successful in creating this theory. The phase diagram also shows a couple of interesting features. You can get both fluid ECT crystal coexistence, fluid HCP coexistence, but this region where we have two solid phases in equilibrium. This even has a eutectic point where a fluid phase and two crystal phases all simultaneously coexist. So I think we've done a good job at developing a theoretical and computational framework for field-directed assembly. So as I mentioned before, unless you're very careful, usually what happens when you try to assemble a crystal is something like this, where the material arrests with lots of defects. By toggling the field on and off, we can anneal out all of these defects and end up with a very high quality crystalline phase. The toggle parameters, T on and T off, it's the amount of time the field is on, the amount of time the field is off, are really crucial to determining the dynamics of these dispersions. For example, if we pick a different value of T on and T off, we can still form crystal, but with a totally different kinetic mechanism. In this case, we formed crystal directly in the fluid through a one-step nucleation mechanism. In this case, we nucleate fluid first, and then crystal within the fluid, two-step nucleation mechanism. So the toggle parameters are crucial to choosing which mechanism is observed. Usually we'll normalize T on to this quantity called the duty cycle, which is normalized between 0 and 1, which reflects the fraction of time in which the interactions are left on. So we can use the field strength to control the dispersion, which is the only control knob we have available if we just keep the field steady. But now with the toggle assembly, we can use the field strength or T off or T on. So we have lots of different control knobs. And we find actually there's a wide range of parameters where we assemble really high quality crystals as compared to what something in the steady field looks like. We can even assemble phases like this fluid-fluid phase that are never observed with steady interactions. So these assembled materials are not true equilibrium states. When the field is on, particles are driven into the dense phase. When the field is off, they're pushed back out into the dilute phase. So there's always particle flux, and particles are always moving in these toggled fields. We have this cyclic driving force going on. These materials are always out of equilibrium, but they do evolve into a periodic steady state where these two fluxes exactly match. And the material doesn't really look like it's changing from cycle to cycle. We showed in a couple of papers that this is achieved when the time average of the chemical potential and the time average of the pressure in each of these phases is equal. We can construct these time averages. So when the field is on, the equations of state look the same as they would if we just had a steady field. From our thermodynamic model that we had before, we can compute this equation of state. It has a hard sphere portion from the reference state, and then a portion that goes as the square of the applied field. When the field is off, the suspension just looks like a normal hard sphere dispersion, and so the equation of state is known. And if we take the time average of these two things, we get back basically a normal equation of state for a steady field dispersion. But now the field strength is scaled by a factor of the duty fraction. So this looks like an effective field strength. That means that the same sort of phase behavior should occur, but now it's this combination of the field with the square root of the duty fraction, of the duty cycle, that's controlling things. And if we go and do simulations at a variety of different field strengths, T-offs, and duties, you see that everything collapses down in terms of a single parameter. And that phase behavior also agrees really well with what our thermodynamic model predicts. So even though we have all of these different control parameters, it's an out of equilibrium system, we're able to leverage equilibrium equations to predict the non-equilibrium response. Okay. So another sort of assembly behavior that we observe is this phenomenon that at high densities, if we start with a dispersion that is in a BCT crystal and lower the field, it will want to transform into an HCP crystal. These lattices are incommensurate. This is cubic and this is hexagonal. So the only way to perform this transformation is by melting a portion of the BCT crystal and then nucleating HCP. A lot of kinetic barriers here, and since this dispersion is so dense over here, the kinetics are very slow. So the dispersion doesn't do this. Instead, it changes from a BCT crystal to a BCO crystal, which can be done with a continuous deformation of lattice parameters. So you can see that there's sort of an easy way to move the lattice around to get to this state. So this has spontaneously broken symmetry, which is peculiar, but somehow looks like a compromise between these two crystal structures. It's a little bit more open than BCT, so it starts to get some HCP flavor, but is easily accessible from BCT. So this can be performed with a steady field if we nucleate BCT first, and then do a lattice deformation to HCP. It's 2 steps. In the toggled field, we actually observe the BCO crystal nucleate directly. So if we're in this region here, even though the steady field should nucleate HCP crystal, the toggled field can nucleate this BCO crystal. And the structure of the BCO is precisely that we would get from the 2-step mechanism in the steady fields. So in some sense, we've formed this complicated crystal, but through an easier mechanism. That's pretty powerful. It's also nice because in order to get a stable crystal through steady interactions, you usually have to add on extra sort of forces in addition to the dipole. So here, dipoles plus an electrostatic repulsion has this small region where it can form BCO crystal. But now you have to engineer 2 energy scales and a length scale, whereas forming a BCO crystal with a toggled field's single energy scale, you just have to control these kind of external toggle parameters, which is easily done. So I think this really demonstrates the power of toggle fields that can make pretty complicated structures, but using simple particles, and can make these structures quickly and at very high quality. So changing gears a little bit, toggling is not the only way to vary the field in time. Another effective mode of time variation is rotating the field direction. So here's the schematic. The field is rotated, and particles will align with the field, and then the aligned chains rotate along with the field. This is often used for mixing at the micron scale. It can be used to propel artificial microswimmers. It can also be used to transport passive cargo. But I think a particularly effective use of the rotating field is when it's used in conjunction with magnetophoresis. Magnetophoresis is the phenomenon where a particle with an induced dipole moves in a field gradient. So if you place a bar magnet, the particle will move towards the magnet. So this kind of setup has been proposed for drug delivery applications. The idea is to load these magnetic particles up with drug and use a field gradient to shuttle them to a target site. Usually these target sites are within really dense, porous tissues. So we can run into problems where particles aggregate while they're undergoing magnetophoresis and then have difficulty actually penetrating through the porous network. This video here, you see that even though the gradient is moving upwards and wants to push the particles through, because they've all chained up, they can't enter the pore. This makes this application not very viable yet. But with rotating fields, increasing the frequency high enough can actually break up the chains. Basically, as you rotate faster, you're increasing the shear forces that tend to slough off particles. And if you use the rotating field with a sustained gradient, you still have the phoretic motion, but now you've completely suppressed particle aggregation. And so these particles can permeate through the porous network pretty easily. And if they were carrying a drug, they could deliver it to the target site. This seems like it's a pretty viable application, but really requires us to know a lot about the transport of these things in rotating fields. And that's never really been investigated before, even in just the bulk suspension. So that's exactly what we wanted to look into. This was done by a talented undergrad, Julia Colon, and we had some help from a collaborator at Northeastern, Randy Erb. So Julia simulated lots of these dispersions in bulk rotating fields, and then computed their long-time self-diffusivity. Basically a measure of how fast these are moving around. So what she found was that as the aggregates break up, the diffusivity tends to increase, but only to a certain extent, and eventually it goes back down. So there's this region of intermediate frequencies where the particles are moving actually diffusing a lot faster than you might predict from their isolated Stokes-Einstein diffusivity. So we thought there might be a couple mechanisms that were responsible for this. One is a hydrodynamic mechanism where these chains act as little stir bars that generate mixing flows that move particles along. Another is chains are interacting with each other, they can bump into each other, and so a particle can hop from chain to chain. So to isolate which one was dominating, we could turn off hydrodynamics, which basically shuts off this mechanism so that diffusion is only due to this interchain mechanism. And that's the case of these X simulations. There's a lot of data here, but you can see this peak, these like red and yellow circles, only for the circles. So the simulations where we shut off hydrodynamics didn't show this diffusivity peak, which made us think that, okay, this was really a hydrodynamic mechanism that was responsible for this enhanced diffusivity. So we also wanted to characterize the magnetophoresis, and really the important quantity here is the magnetophoretic mobility, which relates an applied gradient with the average velocity of the particles moving. Rather than simulate magnetophoresis directly, if the gradient is small, we know that the structure, it won't perturb the structure very much, the structure from a normal simulation with no field gradient. So if we just simulated bulk suspension, figured out its structure, we could infer what this magnetophoretic mobility was. And so Julia did that, and she saw sort of the opposite trend of what the experiments found, where in the bulk, particles actually move a lot more quickly in a magnetic field gradient when the frequency is lower, when there's steady fields. And as they break up in the rotating field, the phoretic motion slows down. It's like the exact opposite of what the experiment showed. So there must be something about the nature of the porous material that's changing things qualitatively. So we consider just a very simple model of a porous material, where if this material wasn't here, the particles could move magnetophoretically in a certain time. But every time they run into an obstacle, they get stuck. And the only way they can move around the obstacle is by diffusing through. So by combining both of these, we can get an estimate for how fast the particles should go through. And that gives us an expression for the effective magnetophoretic mobility in a porous medium. This depends on the bulk magnetophoretic mobility, but because of this diffusion, it also depends on the diffusivity. So there's a prefactor here that depends on the nature of the porous material and also on the Peclet number that determines whether the bulk phoresis dominates or the diffusion dominates. So if this combination of parameters is large, we see the opposite trend of the bulk, where rotating the field enhances the magnetophoretic mobility. So this is a lot more consistent with the experiments. There's a lot of other things we're neglecting here, but we think that we've identified basically one plausible mechanism for explaining why we see enhanced magnetophoretic transport and enhanced diffusion in these rotating fields. Okay. So in this last part of the talk, I want to talk about an intermediate case between these two simulation models. So we've been focusing a lot on this coarse-grained approach where the solvent that these particles are immersed in is completely structureless. This isn't always appropriate for many applications. For example, in electrolytes, within the solvent, there's lots of ions, and these ions structure and really dominate the transport and properties of colloids. And it's important to know how this works because electric fields are one of the most common and simplest ways of controlling particle transport. You're probably all familiar with electrophoresis of a charged particle. The ions can also impart a body force to the fluid and can generate flows like an electroosmotic pump. And because the particles can polarize and acquire induced charge, they can do things like act as electrodes and generate local flows around them. So I'm going to tell you about a new mode of electrokinetic transport that we observe that kind of has flavors of all three of these things. So before that, I have to describe what has changed about the model. Now we have both colloids and ions. So ions are explicitly represented as small beads, and colloids are represented as collection of beads constrained to the colloid surface, and they move together rigidly. We still don't model the solvent explicitly, but we do account for its effect on everything implicitly. In general, we know all the charges on the net charges of the colloid and the charges of all the ions, but because the colloids can polarize, we don't know the surface charge distribution. In the simplest case, and the one that we considered, the colloids are conductors, which means that the potential of all the beads is the same everywhere, the same for a given colloid. We also know that any induced charges must sum to the known net charge. We can couple these two things by considering bead-bead interactions, which relates the potential of a bead to the charge on all the other beads. This is basically normal Coulombic interactions, here just written in in wave space for the periodic simulation geometry. Of course, all the beads still interact hydrodynamically. We have to impose a few extra forces to ensure that beads belonging to a colloid move rigidly. So because we have to solve for this surface charge distribution at every single time step, like the mutual dipole model, these kind of models are also pretty expensive to incorporate into simulations. But again, we did a lot of careful work to derive an efficient method to solve for this charge distribution and parallelize it for the GPU. Makes it really good for these sort of simulations. Now, because we're incorporating all these ions, our dimensionless units have kind of gone to the small scale. So now lengths are scaled by the ion radius instead of the colloid radius, and so on for time and charge. Okay. All All right, so let's look at how the electrolyte affects things. So we have a particle in an electrolyte, and we suddenly turn an electric field on. The particle is going to polarize, like we saw before. But now, because these ions are mobile, negative ions in blue are going to be drawn towards the positive induced charges. Positive ions in red are going to be drawn towards the negative induced charges. And the double layer around this particle is going to polarize. As the ions approach the surface, they'll induce additional surface charge in the particle, which will bring more ions in. And so the dipole moments of the particle and the ions charge up over time, and over a time scale, it's called, of course, the charging time. Okay. So here's a video of this charging process happening. If we look at the angle of the dipoles relative to the applied field, the particle dipole is exactly aligned with the field, and the ion dipole is exactly opposite. If we bump up the field strength, something else happens though. The particle begins to charge up, but an instability occurs, and the particle breaks symmetry and begins to rotate about an axis orthogonal to the field. The dipole is no longer aligned with the field, but it's off axis, which provides an electrical torque that sustains this rotation. This is a well-known phenomenon that's called Quincke rotation. An interesting thing about this Quincke rotation is, well, the video stopped, but the rotation actually facilitates transport of ions. You would have seen blue ions streaming past this way, oh, there you go, and red streaming past this way. So it actually gives rise to a significant enhancement in the electrolyte conductivity compared to the pure electrolyte alone. So here's the same video. This colloid is going to just rotate in place if it has no net charge. But we can add a net charge, in which case it's going to move electrophoretically in addition to its Quincke rotation. These two things couple together, and they actually drive the particle to move orthogonal to the field. They drive the particle to move orthogonally to the field. This is a phenomenon we're calling the electrohydrodynamic Magnus effect, because it's analogous to the normal Magnus effect at higher Reynolds number, where a spinning and translating ball experiences a lift force that veers it off of its main path of rotation. So this is like topspin in tennis or a curveball. But obviously the physics are very, very different in these two. So we'd like to have a continuum understanding to describe what's going on here. And Quincke rotation, these kind of things are often analyzed with what's called electrohydrodynamics using a leaky dielectric model. Leaky dielectric model assigns a conductivity to the particle phase and to the fluid phase, and then constructs basically a charge balance at the interface that you can use to derive all sorts of things. So it leads to predictions that are in terms of these variables. This isn't exactly appropriate for colloids and electrolytes because the colloid is a solid, so there is no ionic flux at all, so that it's hard to figure out what kind of conductivity to assign to it. Also, for highly polarizable particles that have large dielectric constants, you get diverging time scales. This thing would predict no Quincke rotation for conductors, but it's something we clearly observe in our simulations. So instead, we approach this through what's called electrokinetics, where the dynamics and structure of ions are put directly into the model. So we split this into two parts. We consider an inner region very, very close to the particle surface, where the ions distribute themselves as if, according to the Poisson-Boltzmann equation, they distribute themselves as if they were close to a charged flat plate. Far away from the surface, there's an outer region where the electrolyte is neutral, and so the outer potential just satisfies the Laplace's equation. And the inner and outer solutions will match where they meet up. This allows us to construct a conservation equation for the induced surface charge that has two contributions. A contribution from the charge that's injected into the surface by the outer field, and then a contribution due to convection of the rotating colloid. In the linear limit, this has an analytic solution with both stationary and rotating solutions. The stationary solution is stable at low fields, but above a critical field strength, this becomes unstable and the particle will spontaneously begin to rotate. So this pitchfork bifurcation is exactly what electrohydrodynamics would predict, but now the important parameters are in terms of experimentally controllable variables like the particle size or the ion concentration. It's a lot more useful to experiment with this. Another limitation of electrohydrodynamics is it can't produce particle translations. There's no electroosmotic flows that drive the particle to move. So the only way we can compute the only way we can describe the Magnus effect is through the electrokinetic viewpoint. So here's a schematic of this rotating particle. If it has a net negative charge, there's going to be more negative surface charge on one side than the other. So there'll be more ions on one side than the other. The velocity of the particle is related to the velocity of the fluid at its surface. And this fluid velocity basically is proportional to the amount of charge there. So the fluid over here is going to be moving much faster than the other side of the particle. And this is going to propel the particle with a component that's orthogonal to the field. So this is the origin of the Magnus velocity. And we can get an analytic expression for this velocity. It's a little messy here, but this is showing two different particle sizes in different symbols and dashes. And then the lines are this theory, and the symbols are the Magnus velocities we extract from our simulations. So below the critical field, when the colloid is not rotating, everything is symmetric, and you don't get any break. You don't get any orthogonal motion. There's no break in symmetry provided. But as soon as you start rotating, the Magnus velocity starts increasing and eventually plateaus out. Actually, these plateau values agree pretty well with what we observe in our simulations, and it's kind of surprising because there's a lot of assumptions to describe this complicated process, but it seems to do a pretty good job in recreating what we see. The useful thing about this theory is it lets us predict some quantities that might be important in experiments. So we can interpret this critical field as a voltage drop across the particle. This occurs when that's about 70 millivolts. So that means for a 1 micron particle, the critical field is about 700 volts per centimeter. For a particle with a net charge of about 50 millivolts, this means that the Magnus velocity is on the order of millimeters per second, which is really fast for particles of this size. So I think we have like a pretty good understanding now of how this Magnus velocity works. So this lets us investigate further. For example, we know that if the particle has a negative charge in a field, sorry. Sorry, this happens sometimes. Very old. Okay. So we have a negatively charged particle that's moving electrophoretically in the field direction. It's also rotating about an axis orthogonal to the, it's pointing out of the screen. The Magnus velocity is orthogonal to both of these things and obeys a right-hand rule. If we flip the field direction, the electrophoretic velocity switches, the axis of rotation switches, and these sign flips will cancel out in the right-hand rule, and so this Magnus velocity is unchanged by a sign flip. This means that if we have an AC field where the field is constantly flipped up and down, this Magnus velocity should persist over many cycles, which is exactly what we observe in our simulations. Here in the side view, you see the particle moving up and down as the field changes directions. There's no net electrophoresis, but in this top-down view, the Magnus velocity persists over many cycles. This means now that the transport is frequency dependent. At low frequencies, the particle has enough time to charge up, trip the instability, and we see this Magnus motion. At high frequencies, the particle doesn't have enough time to charge up, Quincke rotation is never tripped, and there's no net translation at all. And indeed, if we observe the angular velocity and the translational velocity, both of these go to 0 as the frequency increases. So this means that the charging time is really the critical parameter in setting where this critical frequency occurs. Besides a little plateau region at low field, the charging time decays 1 over the electric field strength. Basically, things are limited by how fast the field can electrophoretically transport ions to the surface. This means that if we do these frequency sweeps for an increasing field, we should observe the critical frequency where things drop off to 0 to be a linear function of the field, which is almost exactly what we observe. So there's many examples of motion orthogonal to a driving electric field. They all stem from this concept of broken symmetry. Usually the broken symmetry has to be specifically engineered into the system. So using particles of anisotropic shape, anisotropic dielectric properties, or particles near weird boundaries like a ratcheted microchannel. Here, I think the power of this electrohydrodynamic Magnus effect is this occurs for isotropic spheres in the bulb, with the Quincke rotation instability providing the broken symmetry needed for orthogonal motion. So we think this has a real application as for active matter. So because this Magnus velocity is decoupled from the field, it acts as a self-propulsion. So this particle appears like it's just a spontaneous swimmer. Quincke rollers near a wall are already used in active matter, but this is a way to generate an active matter dispersion in the bulk. So the dynamics of these particles are entirely characterized by 2 values: the swim speed, which is just the Magnus velocity that we have a theory for. And so this particle will swim at a constant velocity, but rotational diffusion will eventually cause it to wander around with a characteristic reorientation time. This is what's called run and tumble dynamics. This can be cast in a form where the particle runs for a time, tumbles to a random orientation, and then runs again, tumbles to a random orientation, runs again. The long-time dynamics of this are diffusive, and there's a way to represent the effective diffusivity in terms of the run speed and reorientation time. The effective diffusivity you can see is way, way higher than the normal the Stokes-Einstein diffusivity of these particles. And I think you can see in this inset here, this blue and orange curve, you can see the scales. These don't really move very far from regular diffusion, but you can see that these particles are really traveling a lot more with this active diffusivity. We can compute the diffusivity here, shown in from our simulations, which is this column, and compare it to the predictions from these run and tumble dynamics with our electrokinetic theory. And we see that, especially at lower net charges, we actually do a pretty good job at predicting the diffusivity we see. It's only a factor of 2 or 3 off, which for how complicated this is pretty surprising. A lot of other things are occurring at higher charges, and so these estimates get off. But this theory seems to be decently successful at describing this interesting nonlinear transport that can be leveraged for active matter. So the final takeaway here is the sense that we can use external fields to not only assemble things, but to drive assemblies out of equilibrium. Out of equilibrium assemblies are very, very effective at optimizing, for example, their assembly properties in a toggle field, or their transport properties, like in a rotating field. And in addition to, we can use the time dependence of the field to drive things out of equilibrium, or we can use the field to impart activity, which drives things out of equilibrium. And so I hope that this thesis project did a good job of laying the fundamental theoretical groundwork that can describe sort of generic features of all of these things. So that's the end of the science part. I have to give a bunch of acknowledgments to the people that made all of this possible. So first and foremost, my thesis advisor, Jim. It's safe to say that none of this would have happened without your support. Jim has got to be one of the best advisors in the department. I mean, it has been so easy working in your lab, and I've enjoyed it so much. I really appreciate how much time you given to all the students, and we really like value mentoring. That's something I think is incredibly important for a graduate student. As you mentioned, I'm also trying to go into faculty after my postdoc, and I hope I have an advising style that's like yours. You see you as a real role model. I also want to thank my committee members, Professors Weinstein, Serrano, and Alexander Katz. You've really put in a lot of time over the past couple of years to make sure this project was successful, and I really appreciate you for that. I also had the privilege of getting to take classes with every single one of these people, so not only in a research sense was I helped, but also in a classroom sense, so thank you so much. A really fun part of grad school was getting to work with 4 really talented undergraduate students, Helen, Stefan, Deep, and Julia. I definitely wouldn't have been able to get as much done as I did without helpers to do a lot of the research essentially for me. So, you know, having more people, 2 people makes a big difference. So I got 4 helpers, which was really amazing. I also want to thank some collaborators. So I've only done basically theory and simulations. So I oftentimes don't really know how to interpret things from an experimental point of view. So working with Fleet Chen, Pat Doyle, and Randy Erb from Northeastern really, I think, helped ground me a little bit into what are experimentally relevant problems, what are some challenges in experiments, and how to think of things in terms of real, actual material. So it has been a pleasure working with you, and I really appreciate it. The whole Swan Lab has been so much fun to be in, and just a great group of people. So me, Zhiggy, Gong, and Andrew were in the first cohort of students that Jim took into his lab. So it was kind of an interesting experience navigating our research, but also building up a lab. So you can see this is one of our first days where we set up all of the GPUs and CPUs in our cluster. So we got to see like exactly how these things are built and installed. And then we've done a lot of conferences and group activities. So it's been a really fun time working with them, and I've really learned a lot from everyone else in the lab. Of course, we had more people join: Sam, Kevin, Jerry, Kelsey, Emily, Kyle. Special shout out to Jerry for putting together this live stream. But I know that the lab is in really excellent hands. I'm really excited to see the research that you all will churn out the next few years. So, of course, being in grad school is not just about grad school. I think people would go crazy if they were just working all the time. So it's really the friends and the connections that you make along the way that I think really can make it or break it for you. And so I want to thank just all of my friends for just being a constant source of fun and laughs and ways to take my mind off of research. And in particular, I want to name out a few people. So first, Cameron. Yeah, so Cameron and I met a really long time ago on the visit weekend, so even before we came to grad school. I thought we had a really good connection, and then we met again on another visit weekend because he completely forgot who I was. So we made up, and now we're really great friends, and we always have so much fun together. We know how to push each other's buttons, and I wouldn't have it any other way. Sam, I've interacted with in many different ways. So I just dated him, and then he joined the lab, and then we became friends. That we did. A lot of like really fun experiences and adventures together. He's a pretty funny guy, so it's been really interesting to hang out with you all the time, and I've had just so much fun with you. So I really appreciate your friendship. Aaron and Aurora are next. They are some of the most amazing people I've ever met. They're the perfect combination of just very, very brilliant, but somehow can be a complete mess sometimes. So I mean, there's too many moments to count with you guys. Beyonce parties, wine and feels, H Mart surprise. Like, I could just keep going on. Every single memory is like better than the last. So, thank you so much for making sure stuff like this always happens. It's been very, very amazing. And of course, you can probably tell by the number of pictures that Carrie is very important. She was also basically in every other picture that I put. Here's extra ones. Carrie has been my best friend here. We TA'd together. We've lived together for 4 years. So I've probably spent the most time with you as anybody I have in almost my whole life. And I can honestly say I don't know how, I can't imagine doing this with anyone else besides you. It was so easy to hang out with you, and you were there in any capacity, whether I needed emotional support, whether I needed to vent, technical questions, or just for me, no matter what. So I really, there's no way to thank you that much. So I really appreciate it. Of course, my family. I'm originally from Phoenix, so I've lived on the East Coast for 10 years now. So getting back home can be tough. So like the time I do spend with them is really precious. So I really appreciate that, even though I don't get to see them a lot. Every time I do, all I feel is love. In particular, I want to thank my sister, who is a constant source of inspiration for me. I'm so proud of her. She has so many crazy achievements, and every single one makes me motivated to try to keep up with her. So she couldn't be here today, but I think she's watching. Just know that I have always felt support for you, and I'm so proud of you. And then, of course, my parents. My whole life have been just unbelievable, and I never had to worry about anything. All I got from them was love and sacrifice, and they did anything they can to make sure I had every opportunity in life. And I mean, the reason I'm here achieving my dreams is 100% you guys. So I love you so much, and I owe all of this to you. That I will finish up, and thank you so much for sticking around. A little on the long side.
I have a question. So Zach, some of these are from the thesis and some of them are from your presentation. So it wasn't clear in section 2.2 how these are in random order.
Yeah.
It's not clear how the imposed fields can couple back. The particles can couple back to the imposed fields. And I have another question about this. This is you've taken into account how the particle hydrodynamics can couple to the flow field, but where's the case for necessarily neglecting the either the electric field or the magnetic field, how the particle couples back to the imposed field?
I don't think I quite understand. What
So like
couples back to,
for example,
the field source that's being generated, or
charged particles will locally distort the imposed field. I didn't see how that's accounted for. It's possible that it's accounted for via simulation, but so how do particles themselves in a concentration dependent manner affect the field that they experience?
Yeah. So so these field lines around this dipole are what's called a disturbance field. So it's the difference between the true field in the dispersion, which is changed by the presence of the particle, and the difference between that and the external field. So it can be thought as being sort of generated by the particle dipole, but it really isn't. It's induced by this external field in the first place. So what you do is you add the external field plus the disturbance field, and this is the modified true local field near the particle.
But
it's only approximated to the dipole level, You could add fields due to quadrupole, higher order moments, things like
So
that.
so that's the field, just so I understand, that's the field that's distorted by other particles. But what about the collection of particles that the field is propagating through? So isn't there your opposed E0 actually has a mean fluctuation or a mean gradient through the, I don't see how that's accounted for.
Yeah, so that's not, so the, yeah, there's no, like, the field everywhere is completely constant. There's no gradient and there's no, the dipole strengths of these things don't feed back and change the actual field. So this is the constant external field, but it's not, there's also like a flux too. And that's, I don't know if that's what you're talking about, that's definitely varying. I mean, the equivalent things for the magnetic case, this is like the H field, and then the B field is changing, but the H field is constant. So
Like,
I don't know if that's what you're,
the analogy in the electric field is that
dielectric
the particles themselves would be screening the field, right, and going through. So it's not clear how you're accounting for. So here you're accounting for particle interactions, but not the coupling of those particles back into the field. And I think it's maybe you've just
so you're talking because like you're talking about basically figuring out what the field inside the particle is that?
Yeah, like if I send a magnetic field through a thin sheet of metal, right? So that's and in a way your particles collectively are, they're by their existence they're modulating the field into. I put some clarifications in here because sometimes when you're matching theory and experiment, the way experimentalists set up the experiment, they make it so that the field is uniform and that you're studying under thin cross section.
Okay.
But the contribution matters if we want to take your results and model any real thing. If I have particles in a beaker, right, and trying to enclose a field. So I just wanted to, do you have a way of accounting for that or estimating the size of it?
I don't think so. Yeah, we assume that that's something that's known, set external. There, I mean, I think maybe what you're saying, like you could impose like a field outside of the sample that takes one value, and then these interactions could modify it inside. So yeah, we don't account. So this field would be the modified one.
So say if you're observing the particles in the semi-dilute limit, then I think that this is fine. You've neglected it, except that in this work in your thesis, you're actually always going to the condensed phase.
Oh yeah.
And you're always going to high concentration.
Yeah.
Okay, so I think I've got enough there. Yeah.
Okay. Sorry for not understanding that.
So I'm curious, kind of in the first and third parts, you talk about either a toggle field or alternating field. When you have the rotating magnetic field, could you toggle that as well, either spinning back and forth or just on and off? Or even could you just have a toggle field not rotating with that drive particles through the course?
Yeah, so I wish I should. Randy has done all of the things that you suggested. I don't want to say anything incorrect, but yes, any sort of time variation that disrupts aggregation is going to improve the flux through pores, and basically any kind of time variation is going to disrupt the structure. So yeah, so Randy did rotating fields, he did toggled fields. I think he combined them, like you said, and they all gave improved flux. I don't know which one was the best. I'm not sure if rotating is the best or rotating plus toggle. Like, I can't remember. He has a paper published and he talks about it, but I can't remember.
Well, it looked like your diffusivities with the rotating field were more than 1,000 times the Bayer diffusivity.
No, it's only a couple
It is
times.
only
Yeah,
a bit.
between like a factor of 2 and 5 or something. That wasn't active diffusivity.
That's everything.
Magnus particles. That's thousands times bigger. But
Please.
On the Magnus particles.
Yeah.
So at least as I understood it from what you said, the spinning starts to happen because of an instability, but the direction that that spinning happens isn't really set by anything.
Yeah, completely random. It's orthogonal to the applied field, but besides that, completely.
And then when you have the AC field, it's because of those local concentrations of the ions that continue to make it spin in that same,
Yeah.
like on that same axis, but in opposite direction.
Yeah,
Um,
that's exactly what it is.
So my question is then, if you had a whole sea of these particles, they would all conceivably be moving in different directions, and that's why you're describing it as kind of a diffusion. But at a certain concentration with of colloid particles, would the interactions between them mean that they would move as one, or is that something you've looked at?
We haven't looked at it. The next step in these simulations is to try to put multiple particles in and see how they interact. You have to be careful because you're also fighting against dipolar forces. So there's kind of this interplay. The field needs to be strong enough to induce Quincke rotation, but if it's too strong, you'll just get dipolar assembly, like I talked about in the first half. But experimentally, this can be done. And that's what this is describing what you're saying. So you have lots of Quincke rotators. In here, they're rolling along a wall, but it's a
That's why I
similar
was
sort of
wondering.
thing. So this video might replay. Initially, they're all moving in random directions, but they have hydrodynamic interactions between the two that tend to align them. And then you can see they kind of all roll together in a front. I think this video shows it's like almost a plug flow. You can see just a massive wave go through. So they do eventually all align, and it's a hydrodynamic predominantly effect. Yeah.
I have one question about, so the first part where you talked about this dipole interactions. Are you assuming that the relaxation time is essentially very small so that they instantly polarize?
Yeah, you got it. So there's everything is in the pseudo steady limits. The only time dependence is coming from the boundary conditions on the particle surfaces that change because the particle configuration is changing. Yeah, we're not taking into account any sort of like magnetic hysteresis. We're not taking into account any Mealy relaxation times. We're not taking into account any motion associated with like the finite speed of light. None of that. So the magnetic hysteresis would be the most important effect. And that is something that can become important. It becomes important when, especially for it's not so bad for the steady field because the particles are moving pretty slowly on the order of seconds, and these kind of relaxations are slow. But it can be important when you have the time varying field if those time scales approach like the Neely relaxation time scale. Yeah. So no, we don't have any history dependence in here. It's obviously there in the experiments, but experiments show all the same sorts of behaviors.
And I think it's like if you estimate this, I don't know if you thought about like estimating before they turn the call setup, like if it's far away from the frequency that they apply to the
Yeah, it is because the frequencies are all scaled on and that's not for the electrolytes at the end, but for the toggle magnetic fields. They're all scaled on the particle diffusivity. So for a 1 micron colloid, that's order of seconds. So that's actually a pretty long time compared to these internal magnetic domains. So you usually don't have to worry about it. But again, maybe at these high frequencies or high rotation frequencies, it can start to get some weird effects. But yeah, we didn't incorporate them.
They use these magnetic particles in therapies where the oscillating magnetic field fast enough dissipate heat instead of polarizing particles.
I see, so it's very
Hopefully, they need kilohertz and faster sorts of oscillations in order to get this pronounced.
So can you talk about how you choose these toggle parameters? Like, is this something that you'll just have to like determine by trial and error? Can you like learn them perhaps from like
Yeah.
dynamics? Like,
Yeah, there's Hopefully I have this backwards. So there is a way to optimize this. So okay. So yes, there is a way to optimize it. So there's kind of like two things we learned. So we did like a pretty high resolution parameter sweep. So we saw just directly in the simulations which kind of parameters led to the best crystals, both in terms of like the crystal yield and in terms of the crystal quality. And we saw that whenever things went through that two-step nucleation mechanism that I talked about, the crystal quality and yield were always the best. So this kinetic mechanism usually led to very, very high, this is a measure of like the crystal quality. So the reason that works is you nucleate fluid first. The fluid has no grain boundaries and it's pretty mobile, so it's really easy for this dense fluid to coalesce. Then crystal is going to nucleate preferentially in this dense fluid, but the dense fluid is all together, so the crystal's all localized, and it's really easy for it to grow as a single body, and so you don't get any defects, you don't get any grain boundaries. So this is usually favored at slower toggle frequencies. You need a lot of diffusive motion to destabilize this initial crystal lattice, but you still get some aggregation. So parameters that are a little longer that lead to this two-step nucleation process tend to lead to the best crystal. So I mean, this is not something that we necessarily predicted, but it was something that we observed from our simulations.
So I have a related question. So, and it gets at this. Yeah, this is one public question that I want to ask because it's actually a sum of a couple of questions. It's conceptual and it deals with the interpretation of the thesis. I don't want to steal all the time. I have a lot of questions, but one is that this is a good case. Actually, this is a sum of all together. The field is toggled, but it assumes you can toggle the field off. And I know I brought this up before. In section 2.18, 2.13, you assume only a base hard sphere repulsion, and that's a common assumption. And I know that that improves the ability to numerically simulate. But what that implies is it implies a characteristic length scale cutoff, and your results only apply above that. Because real particles have an unscreenable attraction. It's impossible to make a particle that starts from unattracted. Now that's fine because you're essentially implying large particles here. But if I try to scale your results down, there's some characteristic length where none of this applies. And maybe like a better way in your thesis is to flush all that out ahead of time. Have a characteristic ratio and say all of these apply above that ratio. Incidentally, this is like across the colloidal science field, this kind of like bias towards larger particles, pretending small don't exist. It's arbitrary, but like there's nothing magical about 1 micron. It happens to be the easy observable limit. If I have particles under a microscope, I can track them easy. Anyone can do that. As soon as they fall below the diffraction limit, all these tools I have, I can't observe them. I'm fine with that, but then we have all of this theory in physics that's like that just assumes there's nothing that exists. So that's my one complaint is that maybe the thesis needs a derivation or something that shows for a typical particle, this is the size where the inertial forces scale. You get what I'm saying?
Yeah, definitely. Yeah.
So do you have an estimate for like how small does a particle get where none of this would apply?
So when you're at a few nanometers, that's where things are starting to really, like, even things like and inertia is not important, are starting to break down. But as you said, there's other things that would break down much earlier than that. I mean, there's a lot of things. As the particles get smaller, not only is their hard propulsion's different, but the solvent structuring around them becomes more important. There's, yeah, so I haven't done any estimates about when those are important.
Okay.
As it kind of, it depends so much on each particular experiment because they all have different sorts of surfaces, so different solvents. So, but
It's a little bit larger than single-digit nanometer, though. I'll just say, we're not talking about a very obscure limit. It's
Right.
Probably
Yeah.
hundreds of nanometers.
yeah.
Okay, just much more generally, what are the circumstances when it's no longer justified to replace the Brownian hydrodynamics with an implicit solvent?
Oh, so I guess this is sort of related. So definitely as the particle gets small, when you're breaking like the continuum limit, and actually the discrete nature of the solvent becomes important. That's one thing. Basically, anytime you have structure in the solvent is when the continuum limit is going to break down. So for example, for the electrolyte, where there's a lot of structure, we had to put in explicit things. So there could be other structured solvents that are important. For example, if somehow you had a liquid crystal solvent and the vector field description wasn't good enough, like maybe you needed to account for finite reorientation times, things like that, then this could break down. But I think for simple solvents with particles that don't get too small, and also particles that don't get too close, where you're again breaking the continuum limit, you're okay. So I think most of the experiments that we compared our data to usually use particles that are from a micron to 100 nanometers. Occasionally you get some that are a little bit smaller than that, but not much really below that.
If not, we stand the second.